Thank you, Andy. So yeah, before I begin, I'm just going to go over a little bit of background of basically how I got started with the cluster analysis. So as Andy was saying, yeah, basically in college, I was always kind of fascinated by ensemble forecasting and how, that could be an improvement upon the traditional ways of viewing the deterministic models, and basically that's it. So I went to grad school and basically I took several classes in ensemble forecasting and predictability and got the opportunity to work on a research project where I was exposed to ensemble clustering. So then fast forward a couple of years and I was working at WPC, and in 2017 we started our extended range forecast experiment, which at the time was focused on issuing experimental forecasts for days 8 through 10. So as part of this experimental forecast process, basically we were mainly looking at the ensemble means from each of the various ensemble prediction systems, as well as some probabilistic forecast information. And that was basically our forecast process and how we made these experimental forecasts. So having my background in ensemble data analysis and ensemble clustering, I kind of felt like an ensemble clustering tool could be really beneficial for especially the day 8 to 10 forecast. So as part of that experiment, I basically set out developing the ensemble clustering tools, which were at first just for days 8 through 10. And then basically through that experiment, we had a lot of people from various parts of the National Weather Service in the field participating in that. And I think it basically just spread through word of mouth about the day 8 to 10 clustering. And ultimately, I got asked to kind of extend it to days 3 to 7. Which that's basically how the day 3 to 7 clustering came about, which has been around for a few years now and is starting to gain a lot more popularity with forecasters in the National Weather Service. And then finally, that sort of ultimately led to the work that I'll be presenting today, which is forecasting or making clusters explicitly for QPF and explicitly on the QPF field. So with that, I will transition into my presentation. All right, there we go. Sorry, I had a little issue with advancing the slides. So yeah, basically I'm just going to start out with the motivation for why we're doing these QPF specific clusters. So basically at WPC, our mission is to provide national forecast and situational awareness for hazardous weather events with a focus on those associated with heavy precipitation. So going forward, the National Blend of Models, or the NBM, will be the starting point for NWS precipitation forecasts, with WPC making targeted changes to the NBM forecast in consultation with the RFCs and the weather forecast offices. So what is the NBM? So the NBM is a nationally consistent and skillful suite of calibrated forecast guidance based on a blend of both NWS and non-NWS numerical weather prediction model data and post-processed model guidance. So basically the goal of the NBM is to create a highly accurate, skillful, and consistent starting point for NWS gridded forecasts. And at shorter lead times, say days 1 to 2, the NBM forecast is dominated by short-term high-resolution guidance, for example, the HRRR or the high-resolution NAM. But at longer lead times, day 3 and beyond, the NBM forecast is dominated by the global ensembles. And just to kind of illustrate, I have the NBM 24-hour QPF forecast valid for the 24 hours ending at 0Z on September 2nd, 2021. So for those who don't remember, this is the QPF that was associated with the remnants of Hurricane Ida. So what is the meteorological problem? So the NBM does a good job of blending a large volume of forecast data into an accurate and actionable forecast, but it's sort of a black box. Forecasters crave more information on what went into the NBM forecast, and they also want information on forecast uncertainty in space and time that the NBM doesn't necessarily provide. And they need tools that will give them this information. And to just kind of illustrate some of the NBM probabilistic information that is currently available, I have the NBM percentile forecast for the Hurricane Ida QPF, and I have the 25th, the 50th, the 75th, and the 90th percentile forecasts. And you'll notice also on this figure that I have 2 black dots, one showing the location of Columbus, Ohio, and the other showing the location of Scranton, Pennsylvania. And if you look at the percentile forecast from basically the 25th through the 90th percentile, they're almost identical for both Scranton and Columbus, Ohio. However, we can kind of surmise or suspect that the scenarios where Scranton realizes the 90th percentile forecast are probably not the same scenario where Columbus realizes the 90th percentile forecast. But just by looking at these probabilistic fields, we have no way of knowing that. So the impractical solution would just be to view all the ensemble members that go into the MBM. But obviously this isn't practical because there are 100 ensemble members, and to look at them all would take way too much time. I mean, just glancing at them quickly, you can see a lot of bright colors, but you can't really tell if there's a signal for where exactly the heavy rainfall is going to be. You can just kind of quickly see that there's probably going to be a heavy rainfall event somewhere in the Northeast. So the overly simple solution is to calculate the ensemble mean from each ensemble prediction system and then treat them as possible forecast scenarios. So the benefits of this are that it's simple and it lets forecasters somewhat see the underlying data that went into the MBM, but there's also some drawbacks. It doesn't adequately show the range of possible forecast outcomes, and it also assumes the biggest determinant of an ensemble member's forecast is its parent model, which is not necessarily a valid assumption. And just here for the case of IDA, we have the 3 ensemble mean forecasts from the Canadian, the GEFs, the European ensemble, and again, the multimodal ensemble mean. So you can kind of see the variability, but there's probably a better way we can look at that. So the better solution is ensemble clustering. Ensemble clustering partitions the members of an ensemble into groups of members that have similar forecasts, or in other words, discrete forecast scenarios. Simplifying the ensemble down into a few clusters allows forecasters to dig more into the data and get a more complete information about forecast uncertainty in space and time without that data overload problem. So to assist WPC forecasters in their creation of medium range or day 3 to 7 precipitation forecasts, WPC is developing an ensemble clustering tool specifically for QPF that will align with WPC's workflow and forecast responsibilities. So ensemble clustering, how do we go about clustering? So WPC's QPF clustering tool uses a version of ensemble clustering known as fuzzy clustering. And for those who are familiar with the day 3 to 7 clustering, it's basically the same recipe that we'll be using, but we'll be applying it to QPF. So basically that recipe has 3 steps. The first is to evaluate and interpret the first 2 empirical orthogonal functions, or EOFs, of a relevant ensemble forecast variable over a region of interest. The second step is to use Kmeans clustering on the principal components, or PCs, for the EOFs that create clusters of similar members. And then finally, the last and most important step is to actually view the clusters. All right, so some of the specifics of the WPC fuzzy clustering method for QPF. So our ensemble dataset will be half-degree resolution versions of the global ensembles, which are the Canadian ensemble, the GEFs, and the European ensemble. The relevant variable for EOF analysis will be 24-hour QPF. And this is in contrast to our day 3 to 7 clusters where we are clustering on 500 millibar heights. And then we will have 6 regions of interest. So we will have 6 regional domains over the CONUS: the Northeast, the Southeast, the North Central, South Central, Northwest, and Southwest. And then the last thing is, how many clusters should there be? Well, generally 3 to 5 is a good number. So what we do is we run K-means on the EOF principal components with 3, 4, and 5 clusters. And then we use what's called the silhouette score to determine which of those is the optimal number of clusters. And I'll go into that in a little bit more detail later, but the reason I have optimal in quotes there is because a lot of times it's a bit subjective. And since this tool needed to be automated, we needed an automated way to kind of determine whether 3, 4, or 5 was the best number of clusters, which is why we settled on using this silhouette score. So we're going to apply fuzzy clustering to the 4-day forecast for Ida's rainfall over the northeastern United States. For those who don't quite remember, here we have the QPE, or basically the rainfall that occurred or associated with the remnants of Hurricane Ida for the 24-hour period ending at 0Z on September the 2nd, 2021. So we can see a lot of heavy rainfall amounts over 3 to 4 inches in Pennsylvania and other parts of the Mid-Atlantic. And as in some of those figures earlier, I have those 2 black dots showing the locations of both Scranton, Pennsylvania, and Columbus, Ohio. And we can see that, in fact, in this case, Scranton did realize its 90th percentile MBM forecast, but Columbus, Ohio came nowhere close to that. All right, so the first step is to calculate and interpret the first two EOFs. So a note on EOFs. Basically, it's a data analysis technique that is often used in climate studies as a method for determining the spatial patterns that most efficiently explain the variability of a multivariate data set, or in other words, what patterns are most common in the data set. And it's how we get teleconnections like the NAO, which is just the first EOF of the sea level pressure pattern over the North Atlantic in winter. However, EOFs that are calculated across the model ensemble member dimension, as opposed to that more conventional time dimension, result in modes that show the dominant patterns of the difference between individual ensemble members and the ensemble mean. And for each EOF, each ensemble member will have what's called a principal component. So a note on principal components. So the PCs are the projections of the dominant EOF patterns onto the difference between each of the ensemble members and the ensemble mean. So the English translation for that is just an ensemble member with a large principal component for an EOF pattern will resemble the ensemble mean with that EOF pattern added or subtracted to it. And whether you add or subtract is determined by the sign of the principal component. So again, it's a lot of math, but you don't need to know the math in order to interpret and apply the results of EOF analysis. So to kind of demonstrate this, we will be calculating the EOFs of the 24-hour QPF field over the northeastern US on day 4, which we're defining as 0Z September 1st to 0Z September 2nd from the global ensemble forecasts that were initialized at 0Z on the 28th of August. So those first two EOFs are what we have on this next slide here. The first EOF is on the left and the second EOF is on the right. In both of these figures, the contours, which are in gray, show the multimodal ensemble mean forecast, and then the shading is the actual EOF pattern. So looking at the first EOF, we can see that, well, first let's look at the ensemble mean field, and we can see we have kind of an elongated area of heavier QPF stretching from the Ohio River Valley into Pennsylvania and then further into the Northeast. If we look at that first EOF, we can see that it's basically a dipole pattern with higher amounts over Pennsylvania and lower amounts further to the southwest over Kentucky and Tennessee. So basically what this is telling us is that there are differences in the timing of the precipitation, because you can kind of view this as a long track differences in the QPF field. Looking at the second EOF, we also have a dipole, but we have higher amounts basically to the south over the mid-Atlantic and lower amounts further to the north, kind of splitting that axis of QPF. So what this is telling us is that these are basically like a cross-track differences in the QPF field between the ensemble members. So basically EOF2 is telling us is that there is uncertainty in the north-south position of the axis of heaviest rainfall. And I will point out that EOF1 in this case explains about 25% of the variance in the QPF field, and EOF2 explains about 16% of the variance in the QPF field. If you're familiar with the day 3 to 7 clusters, which are based on 500 millibar heights, generally our first two EOFs explain more of the variance for the height field than these QPF EOFs are explaining. And that's just basically because EOFs, well, the QPF field is much noisier. So the EOF, the percent of variance that's going to be explained is going to be lower. It doesn't mean that the EOFs are less valuable or can be ignored. It's just basically the fact that the QPF is a much noisier field. So we're going to get a lower variance explained, but it's still going to point out those dominant modes of variability in the forecast. All right, so then as I said, each ensemble member will have a principal component for the first two EOFs. And what you can do is you can plot them in a phase space, and that's what we have here. So the principal components for EOF1 are along the x-axis, and the principal components for EOF2 are along the y-axis. And now I've kind of already gone through and clustered them, but let's just ignore the numbers for now. But basically here are all 100 ensemble members plotted in that PC1, PC2 phase space. So now I'm going to go over how we kind of interpret the different areas of the phase space. So coming to the right here, basically the ensemble members in this part of the phase space will have a principal component for EOF1 that is positive. So if we go back and look at our EOFs, we're basically adding this EOF pattern onto that multimodal ensemble mean. So we're having the effect of raising precipitation values over Pennsylvania and lowering them over, say, Kentucky and Tennessee. So in other words, these are the ensemble members that have Ida traveling faster, so moving a little bit faster. As opposed to that, if we go to the left side of the phase space, these are the members with the principal component for EOF1 that's negative. So instead of adding this pattern to the multimodal ensemble mean, we are subtracting it, which has the effect of lowering the rainfall amounts over Pennsylvania and raising them over Tennessee and Kentucky. So in other words, these are the ensemble members that have Ida progressing slower. And then we can do the same thing for the second EOF. So if we go to the top part of the phase space, these are the ensemble members with the principal component for EOF2 that is positive. So in other words, we would be adding rainfall in the mid-Atlantic and decreasing rainfall more on the northern periphery of the precipitation shield. So this has the effect of representing the ensemble members that are further south with Ida. And then the same thing with the negative values for PC2, which are down in this part of the phase space. So these members represent Ida being further north, because we would be subtracting this field, which would have the effect of increasing amounts up here and decreasing them down in the mid-Atlantic states. All right, so then the next phase is to use Kmeans clustering. So a note on Kmeans clustering. It's an algorithm that groups two-dimensional data to minimize distance between each point and the center of the cluster it is assigned to. The number of clusters needs to be specified beforehand, and generally 3 to 5 clusters is appropriate. So to select the optimal number of clusters, we run Kmeans clustering on the EOFPCs to create 3, 4, and 5 clusters. And then the number of clusters that produce the highest average silhouette score is selected. And the silhouette score is just a measure of how similar an object is to its own cluster versus the other clusters. And generally a higher score is better. So we retain that version of the clustering that had that highest silhouette score. All right, so here we have the phase space. And again, we've gone through and clustered with Kmeans clustering. In this case, 3 clusters was kind of predicted by the silhouette score to be the ideal number of clusters. And I just want to pause here to mention, this is one aspect where it differs from the day 3 to 7 clustering. The day 3 to 7 clustering, we just have 4 clusters all the time, and we don't let the number of clusters vary. But what we were noticing with our QPF clusters is we kind of get some of these more funky shapes in the phase space, whereas generally with the day 3 to 7 500 millibar height clusters, they're kind of nicely distributed all around the phase space. But with QPF, we noticed that we were getting some of these more odd shapes, and it made more sense to have the number of clusters be varied based on where how the data is dispersed in that phase space. Because if you kind of look at this phase space, you can see that maybe 4 clusters isn't, forcing it to be 4 clusters maybe wouldn't be a good idea, but we can clearly see that there are 3 clusters. There's one over here that has most of the ensemble members, another down here, and then another over here. So just looking at these clusters, and again, I have the physical interpretation of what each quadrant of the phase space means physically, we can kind of deduce what the physical representation for each cluster is. So looking at cluster 1, it's over here in this part of the phase space. So the thing that all of these clusters have in common is that their principal component for EOF1 is negative. So the physical interpretation is that Ida is slower than the multimodal mean. For cluster 2, we're up here in this part of the phase space. So we have a principal component for EOF1 that's positive, and for EOF2 that's positive. So the physical interpretation is Ida is faster and further south than the multimodal mean. And finally, looking at cluster 3, we're down in this part of the phase space with that principal component for EOF1 being positive, but for EOF2 being negative. So this is the cluster which physically represents Ida being faster and further north than the multimodal ensemble mean. And so the last step and the most important step is to view the actual clusters. And the physical interpretation for each cluster will be readily apparent when you actually view them. So if going through the EOFs in the phase space was a little complicated, it doesn't actually matter, and it's not something you have to look at in order to use the products, because the physical interpretation of each cluster will become readily available or readily apparent when you view them. So for example, looking at cluster 1, that's the one that based on the phase space and EOFs we thought meant Ida was slower, and indeed that's the case. It has the heaviest precipitation held further back over Kentucky and Tennessee. Looking at cluster 2, that's the cluster that we decided meant Ida was faster and further to the south. And indeed, that's what we see, with the heaviest rainfall basically over southern Pennsylvania and northern portions of the mid-Atlantic. And then finally, cluster 3, which was the physical interpretation of Ida being faster and further to the north. Again, just viewing cluster 3, we can clearly see that. It definitely is faster than cluster 1 and further to the north as opposed to cluster 2. And just to get an idea of the support of each cluster, at the top of these panels here, we have some numbers. So C3, that means there's 3 Canadian ensemble members, which is 15% of the Canadian ensemble. G17, 17 of the 30 GEFs ensemble members, so 57% of the GEFs ensemble, and 42 European ensemble members, which is 84% of the European ensemble, for a total of 62 ensemble members, or 62% of our 100-member multimodal ensemble. And actually, if we look at the CCPA QPE, so what actually occurred ended up being much closer to this cluster 2 here. And I think that's important to note because, you know, at this vantage point, it would say like cluster 1 was probably more likely, but cluster 2 and cluster 3 were also plausible. And in this case, cluster 2 is what is closer to what actually occurred. So I think as a forecaster, it's good to be aware of, you know, this is the most likely scenario, but there are several other scenarios that could also come to fruition. And in this case, cluster 2 was much closer to what actually occurred. All right, so putting it all together, the EOFs of 24-hour QPF show the dominant modes of uncertainty in Ida's rainfall forecast. A forecaster coming into work 4 days prior to Ida could view the 24-hour QPF EOFs and immediately see that the greatest uncertainty in the forecast was the timing of the system, with the north-south location of the axis of heaviest rainfall being a secondary area of uncertainty. The clusters based on the QPF EOFs do a better job of showing the possible forecast scenarios and their relative likelihood than currently used ensemble visualization techniques. And this is useful information when making and communicating a forecast and the possible ways that it could play out. All right, so now basically what I presented was a lot of the work that I had done in 2021. And now I'm going to transition into some of the more recent work that I've done. So I'm going to start with just the summary and the future work, and then we're going to go over the future work, which has since been completed. So WPC is developing a QPF ensemble clustering tool to help forecasters dig into the data underlying the MBM forecast to better visualize forecast uncertainty and potential forecast scenarios. So in the future, we wanted to obtain the MBM's bias-corrected and downscaled version of the global ensembles and use them as the base of the tool. We also wanted to perform clustering on discrete QPF objects instead of on the QPF over arbitrary regional domains. Another thing we wanted to do was add clustering on 48-hour QPF to account for multi-day events. And then finally, the most important thing was to host the tool on a publicly accessible website so everyone could, see it and use it. All right, so obtaining the MBM QMD ensemble members. So MDL starts with those half-degree resolution global ensembles that I was showing in that previous example. But what they do is perform a quantile mapping and dressing technique to all 100 ensemble member forecasts of the QPF before incorporating them into the blend. So this QMD is essentially a bias correction and downscaling technique. For MBM version 4.1, supplemental locations have been eliminated from this QMD technique, and this is the version that we will be using because MDL was kind enough to share this data set with us, so we can now cluster directly on the ensemble QPF that goes into the MBM. So I'll be going over an example that's pretty recent from the middle of April. And here is the 48-hour QPF forecast ending at 12Z on the 14th of April, 2022. And on the left, we have the raw ensemble from the half-degree ensemble dataset, which is what we were using before we got access to the higher resolution MBM dataset. And then on the right here is this MBM QMD QPF. So again, it's the mean of the same 100 ensemble members, but this is the raw, and then this is the QMD version that we get from from MDL and what goes into the MBM. So you'll notice that, obviously they look broadly similar, but there's a lot more detail in the MBM QMD. And I'll just kind of point to, especially you can really pick it out with the terrain in the west, like looking at Western Colorado, you can clearly see the terrain showing up really nicely there in the QMD forecast, whereas in that raw half-degree data, it's still pretty blocky and you just don't have that resolution that is necessary. All right, so the second thing we wanted to do is cluster on QPF objects. Obviously, areas of heavy precipitation can straddle multiple geographic regions, so it makes more sense to cluster on objects instead of those arbitrary regions. So we developed an algorithm to identify QPF objects. So the algorithm is fairly simple. So first it analyzes the multimodal ensemble mean QPF field and picks out contiguous areas of QPF that are greater than 1/10 of an inch. Then the algorithm checks the size of the area and rejects areas that are smaller than about 60,000 square miles. And then the clustering algorithm continues as before, but only on the area identified as the QPF object. And then the other thing we wanted to do was add 2-day QPF as well as QPF percentiles. So obviously heavy precipitation events can span multiple days, so it made sense to add clusters for 2-day QPF so forecasters could assess uncertainty for a whole event rather than having to look at 2 sets of clusters for each day of a 2-day event. So the QPF threshold for the QPF identification, or the object identification threshold, is raised to 1/4 of an inch, and the minimum size to qualify as an object remains the same at about 60,000 square miles. And again, we wanted to switch from showing the mean of each cluster to the percentiles for each cluster to kind of give users a better assessment of the range of possible scenarios within each cluster. So we have the 10th, the 25th, the 50th, the 75th, the 90th, and the 95th percentiles. All right, so we're going to do a 2-day clustering example with the MBM QMD QPF, and this is for that case from the middle of April, which was a pretty high impact event for central region. So this is the verifying QPF. So what actually occurred, we can see there was a lot of heavy precipitation over North Dakota, which I believe fell as snow, and they had a pretty big blizzard. But there was also heavy precipitation in the upper Midwest and then further south in the Mississippi Valley area. All right, so as before, we're looking at the first 2 EOFs of that 2-day precipitation field. So on the left is EOF 1, on the right is EOF 2. Looking at EOF 1 here, we can kind of see that, actually, if we go back to this verifying QPF analysis, we can see there was kind of like 2 axes of heavy precipitation. This one in the north that was kind of more oriented east-west, and this one in the south that was more oriented north-south in the Mississippi Valley. So looking at the first EOF, we basically have a dipole that's kind of straddling this first area of precipitation that was more in the northern plains. So what this is telling us is that there's uncertainty in the north-south placement of the northern plains precipitation axis. Obviously, it's not quite as clean as the IDA example. I think there's a little bit of magnitude differences also being mixed in with this first EOF here. But the first order differences is that it's showing uncertainty in the north-south placement of the northern plains precip axis. And then looking at EOF 2, it's more of magnitude differences, as we can see that it's kind of the positive EOF shading here is concentrated in the areas of heavy precipitation from the Dakotas down through the mid-Mississippi Valley. So again, this is more uncertainty in the magnitude of precipitation. There's also probably some differences in the placement kind of mixed in with this EOF as well. But the screaming take-home message is that it's uncertainty in the magnitude of the precipitation. So as before, we have all 100 ensemble members plotted in the PC1, PC2 phase space. And one thing I want to point out, and I thought was very interesting about this case, is that here's all 100 ensemble members in that PC1, PC2 phase space, and we have these circles kind of show the location of the ensemble mean for each ensemble prediction system. And then by definition, the multimodal ensemble mean, if there were a dot plotted for that, it would be right at the origin of the plot, so right here. So one thing that's interesting about this case is that if you look at the multimodal ensemble mean forecast, it actually doesn't really have much support from the constituent members. Most of the constituent members are, on either side of this phase space, indicating there was kind of a bifurcation of the possible forecast scenarios, with a lot of ensemble members being further south with that northern plains precip, and a lot of ensemble members also being further to the north with that multimodal ensemble mean, which is sort of a compromise being between the two, not really having any support at all. All right, so again, we've gone through and we've clustered and we've come up with 3 clusters based on our Kmeans clustering and our silhouette score application. Our first cluster, the physical interpretation, is that it has more precipitation. Cluster 2, the physical interpretation has that axis further south and less precipitation. And then cluster 3, axis further north with less precipitation. But again, all of this will become obvious when you actually view the clusters, which is what we have on this slide here. So in this particular case, if we look at the relative support kind of at the top here, the relative sizes of the clusters were pretty similar. This cluster 1 had about 36 ensemble members, cluster 2 had about 36, and cluster 3 had about 28. So about equal support between the various possible forecast scenarios. Looking at cluster 1 and comparing it to the multimodal ensemble mean, it indeed has more precipitation. We can see a lot higher precipitation values in North Dakota and South Dakota. Oh, and I should add that we're looking at the 50th percentile forecast for each of these clusters, as well as the multimodal ensemble mean. Looking at cluster 3, that's the one that had that northern plains precip axis further south with less precipitation. So again, it's not necessarily less precipitation than the multimodal ensemble mean, but it's definitely further to the south with that northern plains precip axis. And it was having a lot of precipitation over Nebraska, South Dakota, and areas of southern Minnesota and northern Iowa, where if we look at the verification, there wasn't much precipitation there at all. And in fact, cluster 2 ended up being much closer to the mark than cluster 1 or cluster 3, with having that northern plains precipitation further to the north with less precipitation in general. So especially with this northern plains precipitation, it did very well. It basically confined the precipitation to North Dakota, which is what actually occurred in the verification. And then it didn't do too bad with the southern Mississippi Valley precipitation. It didn't do bad with that either. And it kind of brought some heavier precipitation amounts further to the east into Indiana and Ohio, which is what verified and not necessarily what some of the other clusters were doing. So this is one way to look at the clusters where we actually look at the QPF. Another way to look at them is to look at how they differ from the multimodal ensemble mean. And I like to look at these plots because they really point out how each cluster is different from each other and the multimodal ensemble mean. So again, we have this for all the percentile forecasts. We're looking again at the 50th percentile forecast, and the color shading here tells us how different that ensemble forecast or that cluster forecast is from the multimodal ensemble. So the green shading indicates where that cluster has higher precipitation totals than the multimodal, and the kind of brown shading is where it has lower precipitation totals. And again, this is where it becomes pretty easy to pick out the physical interpretation of each cluster. So we'll just quickly look at cluster 2. Obviously, it clearly is further north with that precipitation shield because it increased amounts over North Dakota and extending into Canada, but decreased them over South Dakota, Nebraska, and into areas of southern Minnesota and Iowa. So that's basically it. The last thing we wanted to do was host the tools on publicly accessible websites. So obviously the general day 3 to 7 clusters, that website hasn't changed, but now we have the QPF clusters hosted on a similar website. So basically if you're on the day 3 to 7 clusters, just change it from day 3 to 7 to QPF clusters and you'll basically get the QPF clusters. So with that, I will pause and I will take any questions or comments.
All right, thank you, Bill, for the excellent presentation. Before we jump into some questions here, one thing I wanted to do with this talk was to do a couple of polls, and I want to let a few more people join because I know there's been the ongoing internet issues. So I'm going to throw one. I've got 2 polls here, and we'll see what everybody's response is here. And we'll launch this poll. So the question here is, how often do you utilize WPC's clustering products during your forecast process? And I'll give here about a minute to let everybody respond here. So far, we've got about a third of the votes in. Cool, we seem to be solidifying here on sometimes, so that's pretty cool. All right, I'm going to close this poll here shortly. All right, so that first poll came in with about 25%. We're always, 50% sometimes, and 25% never. So I think that's probably what we'd expect at this point. So, all right, the next one is going to be about, for those that definitely have been using the WPC Ensemble cluster products, do you view the EOFs and the cluster phase space diagrams, or do you just go right to the cluster forecasts? And this is a little different way to do it. I usually do these during the middle of the talk or some up front, but no, like let's try one at the end, see how it goes. All right. We've got about just 10 seconds left here, and I'll close the poll. All right, closing the poll. So that turned out with 30% that do view the EOFs and phase space, and then the other 70% just go right to the clusters. So I don't know, Bill, if you have any comments on the outcomes of those polls at all?
Not really any comments, but that's interesting to hear because I guess I've never actually gotten feedback on that. And I've always been curious whether people were looking at the EOFs and the phase space or just skipping straight to the clusters. Obviously, there's nothing wrong with just skipping straight to the clusters, but that's interesting to hear that most people do that.